مقدمة دكتور هشام. هنبدأ إن شاء الله المحاضرة الأولى للبروفيسور هشام العش. البروفيسور هشام العش هو واحد من أهم علماء العالم في مجال الكمبيوتر الكمي والمعلوماتية الكمية. الدكتور هشام العش حصل على الدكتوراه من فرنسا، اشتغل مع أعظم علماء العالم في مجال الكوانتم كومبيوتنج، وهو واحد من أعظم علماء العالم في الكوانتم كومبيوتنج وليه العديد من البراءات والاختراعات في المجال.
زيدان، من فضلك انا واحد من الباحثين وما نحاولوش باش نعملوا التمجيد والتعظيم، لانه انا بصراحه
تواضع.
لا
انا عارفه
يعني
كويس لانه بيشتغل
لا
معاه،
لا,
فانا
لا
عارف
يا زيدان يعني
هو دايما متواضع. تمام.
يا زيدان من
تحيه
فضلك
للدكتور هشام.
يا زيدان
تفضل.
من فضلك يعني قدم بغير ما تكون موضوعي شوي. يعيشك، نعرفك انت تحبني كثير بس تكون موضوعي شوي.
سامعين الصوت؟
نسمع الصوت. تفضل دكتور زيدان.
قرب هنا، قرب حضرتك هنا. طيب.
تسمع فيها؟ تفضل.
بس شايف دكتور هشام؟ شايف؟
قاعد تشوفوا فيها؟
لا، مش شايف السلايدز.
سلايدز
اوكي.
غريبة. I should share the screen. I shared the screen، ولكن أعتقد أنت لما تكلمت share the screen again. يلزمني نعمل share the screen. اوكي
شير ناو.
لا I'm not able to share the screen. يلزم أنت تعطيني البرميشن.
دكتورة
send request.
طب دلوقتي الكورس تقدر تشيره.
لا اوكي. I can share the screen now.
طب استاذ رجب، فين استاذ رجب؟ شفت استاذ رجب. سامعين الصوت كويس ولا ايه؟ طب انا سامع، اللي انتم مش سامعين.
اوكي.
الناس اللي بعيد هناك تقدروا تجيهم. تعال هنا، اماكن فاضيه.
تسمع فيها؟
تفضل دكتور هشام، تفضل.
اوكي. نجم نبتدأ ولا تحب تقدم طريقة موضوعية؟ ما تقدمنيش بطريقة غير موضوعية بصراحة يعني.
لا تفضل دكتور هشام، تفضل.
شكرا.
تفضل على طول بس عشان وقت. تفضل، يلا سلام عليكم.
Today I will speak about conceptual introduction to quantum physics and quantum information. يعني in somehow I will just give an overview about the quantum physics and quantum information without going into the details. That's just like an introduction, conceptual introduction. That means we are not going to the details, just to have an idea about what is going on in the field of quantum physics and quantum information. So let's begin the outline of the presentation. First part, it will be a quick overview on quantum mechanics. Dr. Jihad is with us. Professor Jihad is with us. He will give the lecture on quantum computing. He will have a big part about quantum mechanics, some details what are needed in quantum computation will be discussed there. So then I will give an overview about quantum information, quantum computing. First, let us begin with I insist about a quick overview on quantum mechanics. So first of all, when you see around you, mainly, maybe let me put it in this way here. Just 1 second. Okay. When you see around you, you can see that you have all the technology, transistor, the computer, phones, and so on. These technologies are the fruit of a quantum phenomena. This is they are application of quantum phenomena. Let me explain. So you know that computer and all these machines based on computation are formed by transistor. And this is the basis of computer and digital communication is the transistor. So that is the transistor. The transistor itself is a product of or a result of application of quantum mechanics to condensed matter. So, and we get this transistor is really a result, as I told you, from the understanding, deep understanding of physics, quantum physics. Here, laser is a very good an example of application of quantum physics. And first laser developed by Theodore Maiman in 1960. And from that, now there is lot of application in medical science, in optical communication. You can see there is more than 1 million kilometers of fiber that allow us to communicate between all the continents of the world. They are able to bring data or to transfer data for phones and internet. So one of the nice application, I mean, medical application, is the magnetic resonance imaging. It's a powerful tool for diagnose diseases, providing image inside human bodies in 3D. So this MRI machine is based on utilization of what we call the spins propriety, which is a quantum propriety of the materials. So GPS. GPS is also based on what we call it atomic clock. So, very simple. That's the GPS calculating the time, multiplying by the speed of light, you can determine the distance. That's what using a GPS. That means we should very precise in time, since the speed of light is 300,000 kilometers per second. That means any small deviation or uncertainty in time give big uncertainty in distance. So the GPS is based on atomic clocks, which is very good clocks, very precise around. I don't know exactly, it's like in order of nanosecond or even less. And that allow us to have a precision. And even with that, sometimes if you go to the GPS, you go to any position using the GPS, all of us using GPS, you want to go to one place, usually is uncertainty of 100 to 50 to 100 meters. Sometimes I'm asking for something and I'm confused which block, which is the things they're exactly the GPS I asked for. So like 50 meters, 100 meters is uncertainty. This because of the uncertainty of the atomic clocks. But if we make better, we will have more precision. But I think with 50 meters or 100 meters is enough to go to the place that you want. It's not kilometers. So let me return to the fundamental things. Very simple thing in physics is the atomic physics. The classical physics. In classical physics, you have a particle, and we're taking the very simple example. Sorry, I am around me some sounds, but I'm trying to avoid the noise here. So you can see for when you consider a particle moving around the x-axis, and you have a force like a car inside moving with the force of the engine. So in classical mechanics, we can determine the position, the velocity, on all this using the second Newton's law. So that's really very simple, determine in the same time the position, the velocity, or all the dynamical property just by using the law, the laws of Newton's. Well, here, let's apply this to the atom system. Let's take, for example, hydrogen atom. The simplest model for the hydrogen atom, that the electron turn around the proton. This is the hydrogen atom. Okay, very simple atom. Most of the atom more complicated than that, but this is the easiest simple model for. Let's consider the hydrogen atom because it's dominating in percentage the universe. Okay. So the classical description of the hydrogen atom is an electron turning around a nucleus, which is the proton. So applying the electromagnetic wave theory, this Maxwell equations on the, you can apply classical mechanics, Maxwell equation, whatever. But the most important thing, that's when you are turning here, we know that's a charge. When it's accelerated, because it's turning accelerated, it will emit energy. Electrical charge, when it's accelerated, is emitting electric energy. That's known from the Maxwell equation, from electromagnetic wave, we know that. So the energy of this electron will be lost, and at certain time will be landing on the proton. That means it's going, okay, if it were like billions of years, we can accept. But the problem is that it's a fraction of second, or the calculation giving fraction of second. People try again, trying to calculate this, but every time, oh my God, this is fraction of second. So that means that is the problem is not the calculation. It's the problem that we need another physics to describe the system. And this another physics to describe the system in order to be coherent with the nature. You know, in physics, when you have a theory, you can propose any theory, but it should be coherent with experiment. So if we see the hydrogen atoms, that's one of the arguments, the solid argument against this classical theory and cannot be applied to the atoms, that the fact that hydrogen atom have existed for billions of years, around the beginning of the universe, after the beginning of the universe, like some thousands or of years after the beginning of the universe, this is the atom of hydrogen appeared. Maybe I'm not certain about the exact value, but let's see. We are sure after 300,000 years of the beginning of the universe has like 2.7 Kelvin. There is stabilization, beginning of formation of atoms and galaxies and so on. So at least we can confirm that we have almost more than 13 billion of years, hydrogen atom have been existing. So that means fraction of second. That's what the classical give on billions. There is a contradiction, as I told you. That is a good argument to think about quantum mechanics theory. Usually, when we introduce the quantum mechanics, we introduce it in another way. We speak about ultraviolet catastrophe and so on. But I want to be simple to give you another way of thinking about the quantum mechanics, why we need a quantum mechanics here. So the theory that became to explain all this is the quantum mechanics. On the beginning of that is the Planck. In 1900, Planck proposed, Max Planck proposed a concept, what we call it, quantized of energy. Let me explain that in a very simple way. When you go to the bank ATM, you want to get money. So usually, for example, in UAE, you have a minimum amount of money that you can get it is, I think, multiple of 20, let's say, or maybe multiple of 100. I'm not sure about it, but multiple of 20, let's say. So that is for you can get, for example, 160 dirham, but we cannot get 150 because your unit is the 20 dirham. If you go to the bank, if you go to the bank, you see your bank account, and you can get, for example, 100 dirham in your bank account, but you can never see 100 dirham, and the unit is the first and half fils. This is not possible. By the way, first is the 1/100 of the dirham. All is the unit in your bank account is multiple of fils. You cannot have like 100 dirham plus half fils. So you have minimum. This is what we call it a quantum of money, or a minimum unit of money that you can calculate from. So for ATM, the unit is 20, multiple of 20 that what you can get from ATM. In your account is multiple of fils. So this is the same for energy. You have like a quantum, the name is a quantum. You have quanta, that's multiple quantum. This is quanta, we call it quanta. This is that what define the energy. The energy is formed by multiple of quantum, the unit of the energy. So this idea was catching Einstein in order to use it for photoelectric effect. So without going into details, but it was very nice idea, but without the details, that one photon coming to the solid state system, it can give possibility to be free one electron, to give free electron. So that's why it can be explaining the photoelectric effect. Sure, this photon should have exactly defined energy in order to allow the electron to be free and to give the current. So this concept that Einstein was using is the quantum ensemble. That's the light is an ensemble of quantum, and that is allowing to have the photoelectric effect. This is get a Nobel Prize for that, and not the special on the general relativity, the Einstein well known for. So Einstein get the Nobel Prize because of the photoelectric effect. Yeah, without going into details, just simplifying. I want to simplify all the things without giving more details in that. So people have a lot of conflict, even philosophical conflict. Is the light, is it wave or is particles? So the concept was really some people they're thinking, okay, the light is a wave. The other one is an ensemble of photons that should be particle. And by Louis de Broglie proposed a concept, what we call it wave-particle duality. What it means that let's consider the electron. A photon is maybe simple to understand, but also electron. So that's just another particle. The electron exhibit a wave property and the particle property. That electron itself is a particle, can be behaving as particle or can be behaving like as a wave. It's like when you have the money, you have two faces with the same amount of the money. I don't know the money here, but maybe here. This one here, you have this one, this. This is the sign. So same 100 dirham, but you have two different faces. It's the same for particle on the wave. Sometimes the considered particle can be considered like electron, can be behaving like a wave, sometimes as a particle. So this is the we will return to this because there is experimental proof of this, and we will discuss this, but I will want to go a little bit with the history. So in 1926, Einstein developed his Schrödinger equation. What is the Schrödinger equation? You know, in classical mechanics, I think there is sound around. Noise sound around. Is someone trying to ask me? Okay. Sorry, there is a sound around. Dr. Zidane, can you mute some people? Dr. Zidane. Okay.
Okay.
Can you mute some people? Okay. Let's continue because I'm very sensitive to the noise. Okay. So in 1926, Schrödinger developed his. Okay. Let's return to share again. Share again. I should. Okay. Let's continue.
لا خلي فين سارة؟ دكتور سارة خليك وسط.
لا you.
Okay.
Okay.
Go ahead.
Yeah. Okay. So, okay. That's this one. Oh my God. Let's see this one here. I am not able to return to my sharing the screen. Sorry for that. No, I'm not able. I don't know what is not able to share my screen. Wait, that's sharing my screen. It's not allowing to share my screen. I don't know what to do. Okay, I stopped the sharing.
You are sharing now. Okay. It was okay.
Okay. We'll continue. That's why here. Okay, that's good. Okay. Oh, I understand. Let me stop. This is the problem is sharing again. And again, sorry for that. Okay. So you can see now, right? You can see now, right?
Yeah, go ahead.
Okay.
Go ahead.
So I told you in 1926, Schrödinger equation developed his equation. Like Newton's law, it's a basic for mechanics or for classical physics in general. Schrödinger equation developed the equation that describe the dynamic of a quantum system. So let me give an example in order to understand. So suppose that you have a money. That's Schrödinger equation describing the wave at initial position on time, and that's giving us the wave at another certain position on time. So let's experiment in very simple way. Suppose that you have a money, that's your wealth, okay? You put it in slot machine, and this slot machine transforms the money to the bottle of water. So you have here money, you put it here, and after certain time, you get a bottle of water. That is your wealth state here. That is when you have the bottle of water is the wealth state after putting the money at the slot machine. So this is the same. You put a wave function in Schrodinger equation, it give you another wave function. This is, it can be considered like slot machine, that's in mathematical sense. So that's what we can understand Schrodinger equation without going into details. That describe the dynamic, this fundamental equation of a quantum system. I was trying to avoid any equation to write. And only the simplest one, I have one or two in this presentation, I was trying to avoid to give hard time for the people. Okay, so if we see now the Schrodinger equation is now considered as one of the most known equation used in science in general. There are 17, that is the most known. Einstein was trying to collect all of them. Is in the close to the Maxwell equation, second law of thermodynamical relativity. You can see this is also very close to what people use it now in everyday life. Maxwell equation is used for communication. So, without Maxwell equation, we are not able to communicate through cell phones and so on. Okay. So now is coming the fact that we have a new theory. A new theory needs to make to be interpreted. And we need to have like a standard interpretation. Between 1920, the development of quantum mechanics, to 1930, Copenhagen interpretation of quantum mechanics was developed. This was the biggest people working in that, biggest scientists like Niels Bohr, Heisenberg, Max Planck, and other. They have tried to develop this interpretation of quantum mechanics. So sure, there is another interpretations like Bohm quantum mechanics, or with Bohm interpretation for quantum mechanics, which is in some sense was coming after this Copenhagen interpretation, based on the fact that the wave that the behavior of the particle in quantum mechanics is like a behavior of particle fluid mechanics, but there is a quantum potential, additional quantum potential. So there is a very simple way to transform Schrodinger equation to something equivalent to fluid mechanics, but there is an additional term, what we call it quantum Bohm potential, so that gives the quantumness of the system. So this is another interpretation of Bohm, but it's not well accepted. So people not use it, even if it was developed later, like in 1950s or 60s, but it was not accepted. So that's why the standard interpretation of quantum mechanics now is the Copenhagen interpretation. And there is a lot of concepts, sure, when we make interpretation. Quantum mechanics totally different, counterintuitive than classical mechanics. One of the intriguing concepts is that the quantum mechanics can predict even the system. We know exactly the initial condition, all what around the system. That means the parameters that are influencing the system and so on, but our prediction only probabilistic is different from classical mechanics. So this means that is that's influenced also the philosophy of in beginning of the second 20th century. So people speaking about before, if we know what is going around us, all the condition we can predict the future. This is the deterministic concept, so philosophical concept. On the quantum mechanics, say no. If you know even all the information around you, all what is around you now as initial condition, all the initial condition, all around the parameter of the system, all the parameters that are influencing the system, we can only predict with probability what is going on in the future. We can only predict the future with probability. So it's totally different concept, changing the concept even in philosophy. Okay, then Heisenberg, and uses the uncertainty principle, which also give more sense to this interpretation of probabilistic interpretation. So if you have here, I think, wait a moment. I hope that is working. I hope that is working. Wait a moment. Is this working or not? Let's return. Yeah, you can see that if I know exactly the position, I cannot predict exactly the position of it, the value of the velocity on opposite way. You can see this here. If you are able to predict exactly the position, you are not able to predict the velocity, and vice versa. So that means there is a compromise. I have uncertainty in velocity and uncertainty of the position in general. So, so this is the uncertainty principle, or the uncertainty principle of Heisenberg as known. So then let's see return. Again, this is against the concept of classical physics. Physics, we can predict exactly the position and velocity with perfect precision at any time. So this is the really totally different concept. And this is one of the intriguing effect in quantum mechanics also. So as I told you, and I was speaking about wave mechanics, or wave function. By the way, Schrödinger equation, when he was writing his paper on his equation, he was speaking about wave mechanics. So for him, it was like a wave mechanics, but extension of wave mechanics. So we use the wave function. Schrödinger equation used a wave function. We should a little bit explain what is this. Wave function is describing the state of the system. As I told you, is if you know the initial state of the system described by the wave function, using the Schrödinger equation, you can predict the state of the wave function. Yeah, sure, with probability. Again, I didn't insisted about before, but I'm insisting now. Okay, the wave function characterizes a quantum mechanical particle, and also its dynamics. So let's return to the wave. What is the property of wave? In order to understand this, very simple to give examples. Wave, we have wave water, we have electromagnetic wave. And the most important of the wave is that the wavelength. Wavelength determines the property of the wave. Wave is an oscillatory function, if you want, or harmonic function. You can see that, like sine or cosine, if you want. And that is the difference between the maximum, the two maxima, is a consecutive maxima, is the wavelength. So now let's take an example of what's happening with wave. What is the effect that is we cannot observe with particles? The effect is the interference. If we create one, you can see here, if we create one wave on second wave, there is interference between them. They create interference between them. This is the map here in the my left down. You can see that is constructive interference, and we can have amplitude plus amplitude escape amplification, or it can annihilate one amplitude with another. One wave can annihilate the other. So that is destructive, we call it here constructive interference on destructive interference. Observe this map or this pattern. It's very important, this pattern to observe. That's just indication of interference. Let's now go to the experiment here, the double slit experiment. There is two experiments done. The first experiment, I will send electron through to double slit, and we want to observe what is in the screen here. They have observed patterns, as you can see here. In classical mind, it's the electron will be going from one slit or the other slit. But here, double slit, and then we have observed interference. Here, this means that is the only way to explain that we have interferences, like this pattern here, is that we have the electron behave like a wave. So now we want to detect which part, if we have an ensemble of electron, which electron go in this direction, which one going to the other direction. So when you observe, we put two detectors here, and you send electrons, you can see that you have electrons, some electrons going here, some electrons going here. The explanation is that the electron behave here as a particle. There is no more interference. So that means if you don't observe the electron behave like wave, if you observe it, it behaves here like a particle. So you have, so electron is particle, is it wave? Oh, this is wave on particle. That's the duality concept of duality is working here. So this electron behave as wave in some circumstances, in physical this circumstance. In this case, you are if you not observe the electron behaves like wave, only if you observe it, it behaves like a particle. So this is really show that this wave particle duality. And by the way, that's experiments. That means showing exactly on proving the concept of wave particle duality. So wave is determined, as I told you, by the wavelength and lambda. And usually the particle, as you know, is determined by momentum, or in particular by the mass. So, but let's concentrate the momentum, mass multiplied by velocity. So you can see the link between wavelength and, but that means the particle and the wave through this equation here. And the most important things here is h. This h constant is the Planck constant. This Planck constant is very, very small, 10 minus 34. This is very important. This is defining really the boundary between classical and quantum. So if h was 1, for example, the value 1 joule multiplied by second, then we will be observe all the quantum effect in our life, in our life. So if we were in, for example, in parallel universe, on all the physics is the same, only that we change this parameter h by 1, then we will observe all the phenomena of quantum phenomena for people. We will see people going through the walls, what's all observation, superposition, all these phenomena we will observe it. All the quantum phenomena will be observed on the level of human in that parallel universe. So this is very important. By the way, we have done experiment. I have participated to make some theory with experimentalists, and we have a particle what we call it trions. And this particle behave has some particularity. We have models and so on. We can model it by classical or quantum. We want to see where is exactly the boundary that can this particle behave as classical or quantum. It's not our goal, but that is one of the things that we have observed. And this was around 0.7 nanometer. 0.7 nanometer is a few atoms. In order to give you some idea, one atom, a hydrogen atom, is around 1 angstrom, 0.1 nanometer. So within almost 0.7 nanometer, that means almost 7 atoms, we have observed a transition between classical and quantum. And that was the goal of the paper is not about the observing of transition, but about things like, but just one of the smallest results compared to the others. We published it in Science Advance in 2019. If someone interested, I can send it to him. Okay. So the transition is really experimentally observed. People sometimes speak about mesoscopic system. That's sometimes some system that means they have transition from quantum to the classical, and that's intermediate. But remark that around nanometer or sub-nanometer, it will be transition appearing. We go from classical to quantum. I need this in order to explain after the other phenomenon. So let's go to the application. I will not go deeper in the concept of quantum mechanics and doing some mathematics, but Dr. Jihad is maybe he could give some what is needed for quantum computation as tools for quantum mechanics. But now we have the idea in general. On the application of quantum physics, you see that the first application of quantum physics is to describe all the atomic system. That's obvious. And then the quantum physics becoming fundamental field. And we're trying to explain the nuclear structure, nanostructures, chemical processes. Also, in biology, people using quantum theory in order to explain the quantum biology. There is 2 known books for that. And I'm happy that to present this paper, which is published in PNAS, from 2013, people trying to describe the DNA as quantum mechanical system. And there is 2 of my friends, they were there, Dimitri and Marlin Scully. they have really developed a theory in order to explain the two-photo excitation in DNA using the quantum mechanics. And there is all other theory describing based on the fact of quantum mechanics to describe the biological system. And that's why we call it this is a field as quantum biology. So another thing that is exotic, that's the people using tools for quantum mechanics in order to describe, also to use it in finance. 2006, that this paper appeared, and there is serious journal papers here. You can see some serious paper here explaining the using of wave function stock market, or you can see Hamiltonian in European options, and even it is speaking about second quantification for stock marks. Oh, that's a serious journal describing the finance the stock marks with the tools of the quantum mechanics. Let me explain something more. That in the quantum, this tool, for example, Black-Scholes model. Black-Scholes model is a model of theory of options used in the field of finance. It's like it has a Black and Scholes both. They get a Nobel Prize in 1997 for their theory. On the theory of options is applied for the bank. They can predict the prices with this theory. And they are two mathematicians. They have get a Nobel Prize in economy due to the fact that they were able to develop a theory based on nonlinear partial differential equation. Let me say a little bit technical things, and from that, using tools of physics, that's a tool of mathematics, but they have used a very nice tool is the what they call it. Sorry for that, because I I am a little bit not concentrated. That is the equation of diffusion there is the equation of diffusion. They have used that in order to have some particular solution. You know, the nonlinear partial differential equation is for it can have these types of differential equation can has one solution, several solution, and no solution. That is known for that. It's not like linear. So they have found particular solution, they applied, and was a successful story. And let's use it like a very small concept of the equation of diffusion for developing the Black-Scholes model. But there is another way to describe all this using the theory of the stochastical theory and using the quantum theory in order to derive again this Black-Scholes equations on solutions, and then was like a few lines. That is, people have developed a very big theory, very large theory in order to arrive to that. It's one of the most complicated theory in the finance, but one of the physicists come with the tools of quantum mechanics to retrieve the result within a few lines using the quantum mechanics to show that's the powerful even the tools. Okay. So now there's another application quantum information is the atomic computing. So so for quantum information, sorry for this atom, sorry for that because I get a phone. Quantum information is one of the application of the quantum physics, and this company, Atom Computing, is in October 2023, they were able to build the largest number of qubits before IBM. IBM, they were able to do it in December 2024, and even you can see that it's a little bit less number of qubits than the Atom Computing. And in that sense, that a small company was able to build a largest quantum computer before the IBM, which has spending a lot of billions, was a shock for the IBM. Or they were trying to develop a lot of other tools on to increase their ability. So that means just by having a very nice way of thinking, the quantum computer could be built up by small company, not big companies. Yeah, still millions of dollars, not maybe close to billions, but here in IBM they spend billions of dollars. Okay, I would like to go now to the application of quantum physics, in particular to quantum information, quantum computing, giving some overview, very quick overview. So in order to do that, let me return to the recent progress in science and technology. Just for a few minutes, you will not see my goal, why I presenting that, but you will see it after, okay? So people willing to go to Mars planet, and they want to build cities there, like maybe after maybe 30, 50 years, something like that, they are trying they are thinking to build cities in Mars. That's strange, but that's a strange idea. But they need to build materials. One of the possibility of the progress in technology and science, that the 3D print. We can print anything with 3D, but we need the ink. And people develop it here, and that's a paper. They developed ink from the sand of Mars. That means for the planet Mars. That means here uh, you don't need anything. You should just print a printer, small printer. This small printer will maybe construct with the ink a big printer or several printers, 3D printers. And then from that, you use the sand in order to build this city. This is a very nice idea in order to not transport a lot of things to the Mars in order to build a city. Okay. This is one of the recent progress in technology. This is like a few years ago. Another thing is the stability, artificial intelligence and stability control. You can see that we have artificial intelligence here, able to stabilize the system. You can see here a dog robot, and I think is even more stable than the natural dog. So another progress is the detection of gravitational wave. You know, uh, people get the Nobel Prize in 2017 because they were able to detect the gravitational wave that the general relativity was predicted. But this is bringing us a new tool, what we call it gravitational wave astronomy. You know, in astronomy, you can detect through light the propriety of the system, like stars or planets and so on. There is also another tool is very important in astronomy is the radio astronomy. Through having the analysis of radio frequencies, you can really determine the properties of stars and planets and so on in another way. And then there is another more powerful tool is the gravitational wave astronomy, that using the gravitational wave in order to detect what we are not able maybe to detect with the two other tools. It's becoming a more powerful tool for us to understand the cosmos on the universe in general. So that's why it's not only to understand and to show that is the Lego was constructed, but also to give a tool to understand what is the universe there. That is sometimes we want to prove a theory, but not only the theory. That is bringing a lot of potential applications, and this is very nice for us to understand the universe in the right way. Okay, there's people, I told you there's people trying to go to the Mars planet, but the Mars takes like around 8 months to, depends of the situation, which would calculate when we have a very time window that can go and so on planification in order to minimize, on both optimal time now, I think around 8 months. People were, this is not nonsense, we should develop, if we want to go to Mars, we should develop more rocket, more quicker. And one of the future technologies almost in the process of being developed is the plasma rocket, which people expected to go in 39 days to Mars. Okay, planet Mars. And then there is one development in technology and science. For that, two women get the Nobel Prize in 2020, one from France and the other one from USA. And that's what we call it gene editing. Gene editing is you can really edit the gene, change the gene. What is the possible application? Species rebirth, like Jurassic Park. We are able maybe within few years to reproduce some species that is never exist, that does not exist now, but were existing before millions of years. That is like we call it species rebirth. That's just really exactly reproducing species that can reproduce the Jurassic Park. They can have, also we can develop plants that are more resistant to the disease just by changing some sequence of DNA, creating cell models in particular to understand the cancer and to see what is the gene for the responsible for the cancer, or how we can repair that, to fix errors in the gene. And that is so in order to avoid, for example, a possibility for newborn to have diseases in the future that is linked to the gene or to the history of parents and so on. So all this is what we call the CRISPR technology. So by CRISPR technology, people using usually optical scissors. That's just you see that's physics of there is very important in order to use. That's very nice also technique. And then another thing, all this emerging technology are a common requirement. What they need really very significant computational power to process the information. All that technology that I told you that's the new technology, they need really a very high powerful computers or supercomputers to treat the information. So we have heavy computation needed, simulation of physical chemical systems, for simulation of the universe, from DNA decoding, from artificial intelligence, for simulation of a complex system, mainly economic and financial system, for detecting or predicting rare phenomena like hurricane or so on, also for astronomy to detect exoplanet or exo system there, also to control the aircraft space. You know, sometimes you go to the airport and you should wait for half an hour or 1 hour because the system should optimize in order to allow flights in one direction or other. On this usually is because there is a very complicated calculation behind that. So that's maybe with more computation we need in order to reduce these problems. So or to manage to have some new results, to have simulation. As I told you, all this is based on heavy computation. But there is another problem for us. We are overflooded with data, big data problem. Let's give you an example. For example, in 2025, we expected to have 181 zettabytes of data. 181 multiplied by 10 power to 21. This is a very, very big number for a year, 2025. We should treat this data. Also, Large Hadron Collider, LHC, is generating around 25 petabytes annually. So if you see the satellites orbiting around us, like for the communication and all for this, all the things, usually they are around in December, as I get information from the internet, 8,400 operating satellites. In average, the satellite is collecting around 2 petabytes per year. So we have big data problem on data processing real or reasonable time. That means I am overflowed with the data, but I should also use a benefit. I should take benefit from that, and I should treat the data in real or reasonable time. Other than that, there are nonsense. I am overflowed with data, but I'm not able to process that. This is nonsense. So I need really to process in real time, or at least in reasonable time, all this data. So we need more and more processing. So our goal is to enhance the computing power, and we cannot have cities for supercomputers. Supercomputers are taking a lot of place, but then we have physical limitation. So we should minimize the physical size of computers. So if you see that, as I told you, and I insisted at the beginning, the computational capability is based on the transistor constituting the classical computer. So we need more and more transistor, and the size of transistor should be reduced more and more. So this is what people were doing in the technology. And then they observed that this is just an observation as empirical law here. That is every almost 2 years, I will say 18 months, the size of transistor reduced by the half. And in that sense, the processor or microchips that have transistor have doubling its ability of processing every 8 minutes. So that's what's happening. This is like a really power law form. So the first transistor, if you return to the first transistor in 1947, it was the size of centimeter size. Now, if you have your phone here, smartphone, I will take a phone that's maybe one of the phone is now maybe not too new, but it's still expensive, is Samsung Galaxy 24. It has 16 billions of transistor there. In this size here, it has really 16 billions of transistor. That means the size of transistor around 4 nanometer. Remark this number, 4 nanometer. We are close to 1 nanometer or 0.7 nanometer. So reducing the size of the enhanced of transistor and reducing the transistor for that enhance sure the computational power, but there is a lot of problem with that. When you put transistor close to each other, this is the temperature effect, heating effect, but we could somehow with thinking to solve the problem, we are able to maybe to solve some problem of that. But the most important problem for the transistor that we are closing now to the quantum transition. In that sense, the system will be perturbed by the quantum effects. And that's a problem. What we should do, researchers are looking on the best alternative. Since we are not able to fight the quantum effect, we are closer to the transition to quantum effect. On the quantum effect where we are getting more and more, then why we don't take an advantage, in our advantage, the quantum effect? And that's as people who are thinking about quantum computing as a very promising technology. So the birth of quantum computing comes from Richard Feynman. And his idea was simple, it's not complicated. So we are treating quantum phenomena, simulating quantum phenomena, and using classical computer. But this is an approximation. If we are able to use a quantum calculator to simulate quantum computing, it will be better. Well, that is the idea. Let's think about quantum simulator, quantum system that can calculate and can simulate the quantum effects or to describe the system. This is the idea of Feynman in 1981. So in order to explain what is the difference between the classical quantum computation, we should return to the unit. Remember, the unit of money is fils, for example. The unit of ATM is 20 dirham. We should return to the unit of data that's used in classical computer or quantum computer. The unit of information that we use is the bits. The bit is very simple. It's nothing than 0 and 1. 0 and 1, you have 0 and 1 bit can have 0 and 1 in classical. We are going to the classical computer. And that is the smallest unit for information, digital information. So, but this is usually is combined in order to get what we call it the characters. So usually you combine, you put 8 bits together in order to form byte. This is what we know in computer when we speak about computer, megabyte, gigabyte, whatever. The mega, 10 power 6, giga, 10 power 9 byte. What is the byte? Byte is like a letter, for example, or character. You have able to have like 256 different characters, including the letters. You can see letter A has this symbol 0111001. If you change one of the, if you switch the 0 and 1, you have the letter B, and so on. That's just an example. You have 256, including the special characters, mathematical characters, so on. So your computer is able, with these 256 characters, to do whatever we do as computation, or to write, and so on. So you remember, so for books, for example, in English, you can see that just the alphabetic letters is enough to describe all what we want to describe. But if we want to introduce mathematical symbols and so on, we need a little bit. This computer can include all these characters, 256 can include the symbol, special symbols, mathematical on the letter. And that's how our classical computer work. And that's the bit is the unit now for any character. And you want to write anything here, you put one letter here from your computer is equivalent to 1 byte. So you can understand when I told you we have 1 terabyte of data, that means we have 10 power 12 letters. We can write 10 power 12 letters or spare or save with 10 power 12 letters means it's thousands of books, maybe millions, depends on the books. You can calculate that our book around let's say 100 of megabytes, or 1:01 gigabyte, compared to terabyte, you have thousands of books, big books. Can be stored without any very, very big books. But if they're small, we can arrive to millions of books in your saving in 1 terabyte. You can understand the concept here in classical. So if we go to the quantum, we don't have 0 and 1, but you can see it as a vector here, 0 and 1. In between, you have a combination. And the wave function is a combination between 0 and 1. This is the difference between the classical and quantum. Is a bit 0 and 1. Qubit is superposition of 0 and 1. On this is we call this amplitude of probability. That means when you count modulus of b squared, that's a probability for 1. On alpha modulus of alpha squared is a probability of 0. So if you want to see, I have wave function, I want to observe, that's the wave function we project in 0 and 1. So I have probability to get 0 when I observe the system, or I have a probability of 1, for example, 0.5 to observe state 0, or 0.5 here in this system if I take the same alpha equal beta, or half probability to get 1. But in general, it's not obligation that alpha and beta are the same. You have superposition. Qubit is in superposition. It can be 0, it can be 1, or any value combining 0 and 1. That is the qubit. So a qubit system, okay, that is nice, but where is the system existing? The system is physically existing in for 2 states: spin up, spin down, polarization of photons. You can have vertical, horizontal polarization for superconductor Josephson junction, and also in many different other types of qubit. For example, using silicon technology or GIS, you can see a paper publishing here in 2018 showing that it's possible to create 2-qubit quantum processor using silicon. And you can have also using the traditional GIS. That's a GIS is used for electronics. And you can see that we are able to create 3 qubits here. This is 2018, but now it's more than that. But showing that it's possible using the technology of electronics. That's what people using to construct transistors and all these electronic components. We can use the same technology. We don't need to switch the technology in order to create qubits, combined qubits. And then there was known. One is the superconductor qubits, and the most of them known is the transmon, and the transmon is used in IBM. That's why it's famous for its using the IBM using the superconductor, the transmon is the very particular part of copper per box. Okay, and then people can use also all opticals. We don't need to have electronics, but with optical we can construct qubits, and people using that in order to realize the teleportation. We'll speak about it after. And then people using trapped atomic ions in order to realize qubits. It's possible. And neutral atoms, that is Pascal, French company, they have were able to have 100 qubits together with neutral atoms, and they are now trying to have more and more with neutral atoms, which is easy to implement in the superconductor, because the superconductor needs very low temperature. I can tell you that the superconductor needing a very, very low temperature in order to be disconnected from the thermal environment. And then people using the diamond, NV center of the diamond, NV center nitrogen vacancy centers for the diamond. You see the diamond is mainly based of carbon, but sometimes is one carbon atom is out and replaced by nitrogen. We call it that nitrogen vacancy centers. So the diamond really, people, if you go to buy a diamond, usually they see if there is a black bond there. If there is black bond, that is the vacancy center. If there is black bond, that means the quality of the diamond is low. If there is a few or very small, the quality is better and better when there is no or almost no vacancies or few. So the bad quality of diamond can be used for qubits, as they can within in there the nitrogen atom inside, replacing the carbon. Also, So all this technology developed, they based on a two-level system. All this system, two-level system, the state 0 and 0 or 1. Technically speaking, we are able to do, but it's not only two-level system, we can have several systems. In order to understand more what is maybe the technology, future of technology can be in quantum information can be, we return to the concept of classical computing. Classical computing, you have the logic, binary logic of 0 and 1. And you know, our DNA is based on 4 letters, T, A, C, G. That's 4 levels or 4 codes, if you want. We call it quaternary code, not the binary logic. And from that, with that, you are able to make we have the instruction of for making living cells, living things in our body. So we know that the nature or our body is much more developed than the classical computer. So the 4 level is much better than the 2 binary logic in order to describe system in classical. So what we were thinking about it, maybe we can use taking advantage of that in order to think about a 4-level system, not 2-level system, quantum information. This is possible to do it with what we call it a quansistor. Quansistor is formed by 4 quantum dots coupled to each other, and then with that we have like a transistor in classical, we have quansistor, and with that we can build a blueprint for a scalable quantum computer. I can say version 2 of quantum computer if you want. This paper was published in 2022 in Physical Review A. So you can have also the link here. You can see the link here, and that's one of our result that we have developed. Is we are not stuck with the qubit, but we can go to the higher level, what we call it qubit. In this case, 4 level, and construct really quantum computer, which has a lot of much better properties than the 2, in particular resistance to the noise, quantum noise, and so on. This paper is very lengthy. You can see it if someone of you. I take some moment in order to show you. If someone want to take the information, there is an archive, but you can get that on search in order if you're someone interested in this paper. So let's go to return to the system of quantum information, 2-level system, and we will concentrate in this lecture about the qubits, the 2-level system. And with that, let me return to the situation, very simple situation. I like this system here to describe the quantum bit. Me as an excited state, I call it state 1, or in the rest state or ground state, I call 0. This is 0 and 1. This is what we see in the nature normally. But if I were in the parallel universe with h equal 1, I will be quantum Hisham there, or I will be quantum Hisham there, and there I am in superposition of a state 0 and state 1, excited state and ground state. Okay. So when one is observed, when me is observed, then I can only 1 or 0. By observation, I will project my state to state 1 or 0. With if we take this state, it's 50%. I'm in excited state, 50% in the ground state. When you observe me, I will be not in superposition, but I will be observed as 50% in the excited state and 50% in the ground state. This is one of the fundamental concept of physics. When you observe, you project the state in one of them. Okay. Now take the other one that I am quantum Hisham with a quantum Z10, and we take a state that is combining us. That's what we call the entanglement state. So if Z10 in the rest, in the ground state, I am in the excited state, or opposite. It's Z10 in the excited state, in the ground state. So what means that? It means usually, as I told you here, I have 50% probability to be in excited state, 50% there, and also Z10. But in this state, if I observe them in excited state, then I am sure without doing any measure, 100% that Z10 in the ground state. Or opposite, if I am in ground state, I am sure I have observed Hisham on ground state, I am sure that Z10 in excited state. So that when observing one state of the system formed by 2 qubits, I can predict the state of the second one. This is very crucial for quantum information. This is what we call it entanglement. This concept is very fundamental for quantum information. Dr. Jihad will clarify in more details these applications. Okay, this power of entanglement get captured by Cho. he developed his Shor algorithm, showing that the quantum computer could efficiently factorize large numbers. So let's take a very simple. In the high school or even before, we know how to factorize numbers. For example, if you have 15, we can factorize by prime number 5 by multiplied by 3. But it's a big number. But if we have a big number, it's a little bit hard to decompose in its prime constituent. So Sure has developed an algorithm for example, I can give, for example, thousands of digits. A thousand of digits is hard to decompose in for classical computer. For example, I gave this arbitrary example, but maybe even more than that. Sure algorithm is able to do that and to decompose in its prime numbers just less than 100 seconds, which usually for current classical computers takes thousands of years. So why is that? Why? This is not only mathematical game or any satisfactory mathematical tool, but that is because all the crypto money, or sorry, the crypto system, or what security for the bank, security for our data, and so based on RSA. Even your credit card, if you take your credit card, if you get your credit card here, so usually it's based on RSA. So that means in order to protect your information and so on. On this crypto system called RSA, does protect you based on the difficulty that's inability in short time to decompose a very big number. So what is if the quantum computer coming? How to should protect our system? One of the possibilities is quantum cryptography. I will speak it in detail after. So quantum computing now is treating the security. A quantum computer can solve problems exponentially fast than classical computer. But it's treating for RSA, that's used for coding, you know, for crypting our information. That is the most powerful technique now used on other encryption standards. It's a potential risk to the digital communication. That means digital communication also is protected. And then if the quantum computer coming, that's all people can hear your communication without any problem. So, and then there is another thing there. People waiting to have a quantum computer, what we call data vulnerability. That's they store the data, and then wait till the quantum computer come in order to decrypt. For example, if you have data that is very secure for the government and should be held secret for 50 years, now, if you bring you store the data there, you get this data encrypted, and then you are not able to decrypt it. On waiting, the quantum computer will be very powerful, maybe 5 to 10 years from now. Then they will be in trouble because the secret that's supposed to be held for 50 years will be no more only for 10 years or 5 years as a secret. On this economic distribution, the disruptions, that means this is with the quantum computer, there's vulnerability to the banks and all these protocols that protecting your money. So it's very important to see that the quantum computer is also giving us hard problem for security on data, on all these things. So what we should do is like becoming a weapon. Is quantum computing now becoming a weapon for nations? So that is urgent need for quantum resistant cryptography starts now. So there is two ways. I told you about the first, the quantum cryptography is based on fundamental laws of quantum mechanics. On the example developed is the BBA 84 protocol, and that is well known, and that is used also. There is another way to do it is in order not to switch from classical to quantum, because I will explain after what is the disadvantage very quick to come from classical to quantum. But there is another way, is what we call post-quantum cryptography. Security is based on difficulty of mathematical problem, even that are hard for quantum computers. The quantum computers that will be appearing in next years, maybe. But for next generation, like a second, third generation, maybe it will be easier for them to decode or to solve the hard problem. Okay, on the examples of algorithms like Crystal Keeper or whatever other problem that we can show that is even with maybe next generation of quantum computer can be resistant. But in any case, we have two types of protection from quantum computing attacks. One is the quantum cryptography, the other one is post-quantum cryptography. So the first one is require specialized quantum hardware. That means we should switch our system to the quantum hardware, which takes a lot of money, a lot of time. It does not encrypt the data directly, but it uses a secure method to exchange keys, that is just by keys, changing the exchange. This is based on quantum physics. That is the two disadvantages. The big advantage is based on physical laws, which is could guarantee the security against any advanced version of quantum computer. Whatever the quantum version of quantum computer, we think that with the quantum physics law, because you are using quantum physics law, this is secure even to the advanced quantum computers, version 1, version 2, whatever. But post-quantum cryptography here has an advantage that can be implemented on classical computer without need for quantum hardware, designed to replace existing cryptographic standards and can be used in internet. This is a big advantage because we can do very quick, smooth transition. However, the mathematical difficulty could be not secure for a next version, advanced version of quantum computer. So maybe we can begin with post-quantum cryptography using some cryptography or switching with transition to quantum cryptography in order to guarantee maybe the security of our data in general. Okay, that is maybe the strategy combining them. One is very quick now to use the post-quantum cryptography, and the other one is to have the quantum cryptography. Okay, so quantum cryptography first was used in Vienna in order to depose 3,000 euro there in 2004. Then they have used it in election in Geneva in 2007. Yes, Jane. So, do you hear me? Do you hear me? Hello? Hello? Do you hear me?
Yes,
Yeah,
yes, Dr.
Go ahead, go ahead.
Thank you.
Hisham.
Yes.
Yeah,
Thanks.
Dr.
Thank you.
Hisham.
Yes,
I'm
warning me.
listening, but watch the time because I have a
No, don't
lecture
worry.
after my lecture in the university. So
Don't worry. I'm almost.
okay, watch the time. Thank you.
Quantum cryptography is now, as I told you, is used as first used in 2004 for 3,000 euro deposit, then in Geneva, in the election of Geneva in 2007. And then China was possible to transfer the data in space to the Earth within 1,200 kilometer distance. Quantum cryptography was used this in 2017. As I told you, the post-quantum cryptography now NIST is working hardly on that. And in August 2024, they have proposed to use 4 quantum algorithms after exploring all the possibilities. And this seems to be the candidate to use it soon in order to be protected for a quantum computer. We call it post-quantum cryptography. And also, now a quantum computer combined with AI will be even much powerful. We call it quantum AI. And the AI, the quantum computing uses the qubits for parallelism to increase the rapidity of the calculation. Artificial intelligence try to understand the patterns designed for tasks like pattern recognition, natural language processing, or decision. Combine both of them, that is the AI, could solve complex problems beyond the classical computer ability and accelerate machine learning and optimization process. So quantum AI is now very, very, it could be very, very powerful tool and also very, very, very powerful trading for security also. So quantum computer, last advances, let's speak about last advances of quantum computer. We have now expected in 2024, we have 4,000 qubit processor that will be realized by IBM. In December 2024, which was shock for IBM on advantage for Google, they developed Willow quantum chip, which is this new chip is resistant to error correction. Is very demonstrate error correction performance, and then reduce the error exponentially by using more qubits. Usually when we put several qubits together, we have more and more error. But this is the opposite in this yellow chip. And then they have tried to they have used it for 5 minutes computation and compare it if how is equivalent in the most powerful for the most powerful computer, which is El Capitan in Lawrence Livermore National Lab in USA. And this most powerful computer in the world now will take what Willow performance has done for 5 minutes, what Willow has done for 5 minutes, will take 10 septillion years, 10 power 25 years. That means much more than the age of universe. The age of universe is 13.7 billion of years. So quantum computing will solve several problems, in particular simulation of physical chemical system, cryptography, drug design, artificial intelligence, financial modeling, logistic optimization, prediction of rare phenomena on space on exoplanets. So we expect that, as you can see, that is the evolution of the computation on the ability of the computer. We expect like around 2035 that we are able to have a computer that is equivalent to human brain ability. This is to the quantum computer. And we expect before 2060 the technological singularity. That means the computer is able to do better than all the human brains together. That's what we call it, technology singularity. That means the computer will be able to take off all and then to control us. That is what people are afraid from that. That is even we become that is science fiction spoke about it, but it could be a real problem in the future. So due to this importance of quantum information, several nations, in particular USA, take attention about it. And you see that is in USA there is National Quantum Initiative in 2018, on National Security Policy paper in 2022, putting all the two presidents, they have signed that, the president before Biden and Trump in his first election part. They were signing about these acts. That is very threatening for them, very important. Europe, for them, is quantum technology is very important. They have a roadmap in 2020. And China in 2021, they defined one of the 6 priorities, that is quantum technology. And then if we are speaking about the worldwide quantum computing, what expected in 2023, that will bring like 4.5 trillion. In order to understand what means 5.3 trillion is equivalent, even larger than the third economy in the world. Japan has 4.2 now, almost 4.2 trillion as GDP. And here we expect in 2030 that's 4.5 trillion. What we bring as wealth for quantum computing is larger than Japan GDP, which is the third most powerful economy in the world. And then we spoke about quantum teleportation. Now we know that the quantum teleportation is possible to do for quantum state, mainly photon. It was possible to do quantum teleportation through satellite with 1,400 kilometers. But if you see here, I don't know if you know Star Trek. In Star Trek, they are in 1960 said that the science fiction series, and they predicted that people are able to transfer one place to another. It's like transportation tools. It's maybe I don't know, but I cannot expect anything in science. We cannot say it's impossible in that time. In this time, we can say maybe 50 to 100 years, maybe we will be transported. This is maybe the most powerful transport from one place to another with instantaneous. Although if you see, this is the future. What the future of quantum computing will reserve for us is beyond our imagination. I would like to say that this is the first introductory part for the lectures, and you can see, I hope that I have a real motivation to study or to be in this in the future lecture. Thank you very much. Yes.
Thank you very much. Thank you very much, Prof. Hisham, for this interesting lecture. Indeed, it's a heavy lecture. It's interesting. It's an overview from the quantum mechanics beginning and through the history of quantum computing and about its applications and quantum computing. It's a very, very rich lecture. حد عنده أي استفسار دكتور هشام؟ اتفضل. علي صوتك بعد إذنك. طب في سؤال يا دكتور هشام. What's the difference between cryptography and post quantum cryptography?
Yeah, that's excellent.
في كمال السؤال؟
اي كمل السؤال. ما نسمعش هيك المشكله.
هي سؤالها في منه تو بارتس. البارت الاول what is the difference between quantum cryptography and post quantum cryptography?
Let me answer to the first part.
What is the lattice rule?
Yeah, that's first quantum cryptography based on quantum mechanics to protect the information. The post-quantum cryptography is to use difficulty of mathematics to be protected for quantum computer. It's totally different. One is the quantum, based on quantum technology in order to protect the information. The other one is based on difficulty of the mathematical difficulty in order to be protected from the quantum computer.
I will explain in Arabic. الفرق بين الكوانتم كريبتوغرافي بس عشان اوضح لزمايلي بس. الفرق بين الكوانتم كريبتوغرافي والبوست كوانتم كريبتوغرافي. الكوانتم كريبتوغرافي انت الكوانتم كمبيوتر زي ما شرح البروف هشام ان هو بيكسر التشفير بتاع اي كلاسيكال كمبيوتر. يعني اول ما يطلع الكوانتم كمبيوتر التشفير بتاع البنوك وبتاع البيتكوينز وبتاع كل التشفير اللي احنا بنستخدمه النهارده ده كله هيتكسر بسبب الكوانتم كمبيوتر. فالبروف هشام انا هوضحها بالعربي عشان اوصل لكم الكونسبت. الكوانتم كريبتوغرافي انت بتشفر المعلومات باستخدام الكوانتم كمبيوتر عشان تحمي المعلومات من الهاكر بتاع الكوانتم كمبيوتر. اما البوست ازاي تستخدم الجوريزمات في التشفير، بس الالجوريزمات دي تتنفذ على كلاسيكال كمبيوتر عشان تحمي الكوانتم كمبيوتر من الهاكر بتاع الكوانتم كمبيوتر.
مش تحمي كلاسيكال كمبيوتر من الهاكر بتاع الكوانتم كمبيوتر. الاولى تستعمل الكونسبت بتاع نتكلم بالعربي مش مشكله. الاولى تستعمل الكونسبت بتاع الكوانتم فيزيكس باش تحميها. يعني الرولز بتاع الكوانتم فيزيكس ولا اللوز اوف كوانتم فيزيكس بروتكتنج ذا انفورميشن. هذه جارانتي. الثانيه هي الديفيكولتي بتاع الماثيماتكس، هي تحمي المعلومه. فاذا كان جاء كمبيوتر كوانتم كمبيوتر فيري باورفول اللي يحل مشكله الديفيكولتي بتاع الماثيماتيكال ديفيكولتي، انتهى الامر. البوست كوانتم كريبتوغرافي اسمه يبدلوا التكنيك مره اخرى. بينما في الاخر وات ايفر ذا كوانتم كمبيوتر جاي ما يجبش يعمل اتاكس على الكوانتم كريبتوغرافي لانه محميه بالطبع بالرولز اوف كوانتم ميكانكس. ولكن الاولى مكلفه جدا والثانيه ترانزيشن دايركتلي، يعني جاست تتبدل البروتوكول فقط، فبالتالي نجموا نطوروها بسرعه. هذا الفرق بيناتهم الاثنين.
نعم برضو يعني اوضح معلومه للطلبه اللي لسه جدد. يعني التشفير في الكلاسيكال كمبيوتر بيعتمد على التعقيد في الماثماتكس. انت استخدمت تعقيد ازاي في الماثماتكس عشان تحمي البيانات، فبالتالي عشان تكسر الكومبلكسيتي بتاعت الماثماتكس دي هتاخد سنين طويله جدا عشان تقدر تكسر الكومبلكسيتي دي. اما في الكوانتم كمبيوتر انت مش محتاج انك تعمل كومبليكيتد الجوريزمز بناء على الماثماتكس، ولكن بتستخدم القوانين الفيزيائيه بتاعت الكوانتم ميكانكس عشان تشفر المعلومات. فالكريبتوغرافي في الكوانتم كمبيوتر محمي بقوانين الكوانتم ميكانكس، اما التشفير في الكلاسيكال كمبيوتر اللي احنا بنستخدمه النهارده ده محمي بقوانين الماثماتكس. فقوانين الماثماتكس تقدر تكسرها لكن قوانين الفيزيكس ما تقدرش انك تكسرها. طيب
هو كده البوست كوانتم كريبتوغرافي الامبلمنتيشن بتاعه كله هيتم على الكلاسيكال
بالظبط. في سؤال دكتور هشام، الدكتوره بتسال بتقول هل البوست كوانتم كريبتوغرافي بيتم كله على الكلاسيكال ولا على الكوانتم؟
شوف، هو الى الحد الان لانه معنا الباور بتاع الكلاسيكال موجود، عندنا ماشين كلهم بالكلاسيكال فيعتمدوا على الكلاسيكال، ولكن هذا لا يمنع ان نجموا نستعملوا الكوانتم تو اكسلريت، مش الكونسيبت بتاع الكوانتم، لانه فما فرق. احنا الكوانتم كمبيوتر معمول تو اكسلريت ذا كالكوليشن، فيعني ممكن تعمل اي بروبلم you send it to the quantum computer to accelerate. مش مفروض يكون كوانتم بروبلم، يعني يجب يكون كلاسيكال بروبلم اوبتمايزيشن. كلاسيكال اوبتمايزيشن يعني سيلز مان بروبلم، يعني واحد يشتري في، تعرف سيلز مان بروبلم شنو معناها؟ معناها واحد بايع باش يتعدى المدن كثيره وباش يبيع في كل مكان، فهو عنده بعيدين عن بعض، فشنو هو احسن طريق ياخذه باش ما يخسرش، باش يكون اقصر طريق بالنسبه له. فهذا سيلز مان بروبلم. وقت تكون المدن كثيره، المشكله شنو الاوبتيمال تراجكتوري اللي ياخوها. فهذه اكسبوننشال بروبلم، سيلز مان بروبلم معروف جدا. فهذا مشكله. بالنسبه للكلاسيكال كمبيوتر نعملوا الجوريثم فيها ابروكسيميشن، ما نجموش نلقاوها بطريقه سهله. في الكوانتم كمبيوتر ما حيسرع الكالكوليشن ويعطينا مور اوبتيمال ولا احسن طريقه باش نجموا نعملوا اوبتمايزيشن. فهمت؟ ولكن البروبلم هو كلاسيكال. نفس الشيء في الكوانت في البوست كوانتم كريبتوغرافي يستعملوا الكمبيوتر او الموست باورفul كمبيوتر او الكوانتم كمبيوتر. المهم بالنسبه لي في التسريع التشفير او في الطريقه السريعه الكوميونيكيشن. يوجولي في البوست كوانتم كريبتوغرافي فيها تكنيك، فما يهمهمش شنو الكمبيوتر اللي موجود، احنا حاجتنا باش نحميو المعلومه كلاسيكال، هي كلاسيكال باش نحميوها. ذاتس ات. يعني بينما في الكوانتم كريبتوغرافي هي طريقه اخرى، نستعملوا اللوس نتاع الكوانتم ميكانكس نرجع باش نحفظوا المعلومه. فهمت؟ هما طريقتين مختلفتين، فهي المعتمده على التشفير. التشفير يجب تسرع التشفير في اي تستعمل اي كلاسيكال ولا كوانتم، ما هيش مشكله، بس التشفير هو كلاسيكال. بالنسبه للثانيه اعتماد على المحافظه على المعلومه بالكوانتم، يعني انت تستحق سيستم كوانتم تو بروتكت الانفورميشن. الاخرى ما تستحقش الكوانتم سيستم باش تعمل التشفير. لو عندك كوانتم سيستم باش يساعدك يسرع في التشفير مش مشكله، بس اهم شيء تحافظ اللي انت تستعمل كلاسيكال كمبيوتر. واضح؟
طب تمام دكتور. اتفضل.
البروفيسور يتكلم عن الكوانتم من الابلكيشنز بتاعته اللي هو البريدكشن للايرثكويكس والفولكانز والكلام ده، هل هو يعرف جروبس يشتغل في النقطه دي ولا لا؟
طب اسمك ايه؟
دكتور رمضان بكير.
الدكتور رمضان بكير بيسأل حضرتك، بيقول لك حضرتك بتتكلم ان الكوانتم كومبيوتنج بيعمل بريدكشن للزلازل والكوارث الطبيعيه.
هو
هو بيسأل، نكمل السؤال. هل حضرتك تعرف ريسيرش جروبس حوالين العالم تشتغل في الاتجاه ده؟
لا، بالنسبه للاتجاه هذا ما نعرفش، اما انا كونسبتوال انا قلت لك يعني ليش نفسر لك الطريقه، ما عندي معلومات بسيطه مش كبيره، مانيش سبيسياليست طبعا. ايش باش نقول لك؟ بالنسبه للكوارث الطبيعيه، منهم الكوارث البراكين والزلازل والاشياء هذه تتطلب تعقيدات فيها كالكوليشن كبيره، فهمت؟ ويستعملوا رير فينومينا، فما ستاتستيك فور، يعني فما علم كامل يعتمد على رير فينومينا، يعني علم كامل في statistics والبروبابيليتي يعتمد على الرير فينومينا، وهذه فيها حسابات معقده جدا، فتستحق كالكوليشن سرعه في الحساب. فمثلا احنا نعطيك اكزامبل باش تفهم بطريقه سهله. احنا نعرفوا الايرث كويك مثلا اللي هو عنده سم سيمبلز، يعني مثلا اذا تشوفوا انتم مثلا كلاب تنجم تتبع بالكوارث بعض الاحيان لانه يعني فيما فيبريشن او شيء، فما ديتكشن، فما اشياء فيها ديتكشن ممكن تقول هذا الزلزال باش يجي. ولكن انا مانيش في كل مره نعمل تحذير اذا كان الزلزال باش يكون درجه واحده او اثنين من سلام ريشتر. أول شيء صارت تجارب نووية بعيدة عليها 1000 كيلومتر يمكن تعمل ذبذبة بنفس الشيرة. فبهذا نحب نتنبأ كم حتكون بحيث أن نتعامل مع الأزمة هذه. فكيف نعمل؟ يلزمني نعمل بريدكشن، الحسابات معقدة وتطلب كثير من الوقت. إذا كان الزلزال بشي نص ساعة وأنا عندي كمبيوتر يعمل حسابات يقعد يومين، انتهى الأمر. يعني يلزمني كمبيوتر في حوالي دقيقتين إلى 3 يعطيني ريزلتس باش على الأقل نحمي الناس اللي موجودين هناك. ولكن اذا كان رايت اللي زلزال التوقع نتاعو درجه او درجتين مش مهم، يعني مش باش يعمل ولا تقريبا ولا كارثه، جاست نحذر انتبهوا نوعا ما وانتهى الامر. بس اذا كان على 7 و8 و9 فيلزمني نخلي في فتره قصيره الناس، فكل دقيقه نخسرها من حياه الناس. فالكوانتم كمبيوتر هو يسرع الكالكوليشن هذه، هذا الطريقه كيفاش نجم نفسرها يعني. بس انا بصراحه مانيش سبيسياليست، بس انا نجم نعرفه اللي كوانتم كمبيوتر يجي يسرع في الحالات الحرجه جدا يسرع. كما انسان مثلا لا قدر الله معروفه زاده في المرض، في واحد ساعات تصير جلطه خفيفه او ضعيفه، بس انت اذا كان عندك سياره اسعاف سريعه جدا تنجم تمنعه. نفس الشيء الكمبيوتر اذا عندك سرعه كبيره جدا في الحسابات تنجم تتنبأ ايش باش يصير، وتنجم بالتالي تشوف شنو الامكانيه التصرف نتاعك بحيث ان تنقذ ارواح الناس بطريقه او باخرى.
نعم، والتقنيه دي بنسموها الديجيتال توين.
آه،
فالديجيتال توين ازاي تحاكي الطبيعه على الكمبيوتر سيستم باستخدام الطرق بتاعت الارتفيشال انتليجنس. فالفكره هنا ازاي نستخدم كوانتم كمبيوتر عشان نعمل الكوانتم ديجيتال توين عشان تكسب وقت، زي ما بيقول بروفيسور هشام، وانت بتتنبأ بالزلازل في فيري لو تايم. فمحتاج هنا الكوانتم كومبيوتنج بتقلل السرعه. طب حد عنده سؤال؟ اتفضل.
انا ما فهمتش الريليشن بين البلازما روكت والكوانتم كمبيوتر.
ما فهمتيش فرق بين ايه؟
الريليشن ما بين البلازما روكت
البلازما روكت.
والكوانتم كمبيوتر.
طب في ناس سؤال بتقول هي مش فاهم الفرق بين البلازما روكت والكوانتم كومبيوتنج.
انا بصفه عامه التكنولوجي اللي وريتهم هما تكنولوجي يعتمدوا على الديفلوبمنت نتاع الكالكوليشن كومبيوتيشن. بلازما روكت تعتمد على حسابات معقده باش نجموا نستغلوها في البلازما روكت. يعني هي البلازما عندنا بلازما سيستم في معادلات معقده يلزمنا نجموا نعملوا حساباتها باش نجموا ونسيطروا عليها وكنترول باش نجموا نستغلوها في الترافلينج. هذه الحسابات هذه لو عندنا كوانتم كمبيوتر يساعدنا باش نعملوا الديزاين نتاع الروكت، وكذلك باش نعملوا الكنترول نتاع الروكت. شوف انت مثلا في دقيقه معينه صارت الروكت نحب نوجهوها نبدلوا الاتجاه نتاعها في نص ثانيه الاتجاه هذا، ثم نبدل نص ثانيه هذه باش نجم نعمل تراجكتوري. لو مثلا نيزك جاي في اتجاه الروكت هذه، فيلزمني نكون انا نعمل حساباته بسرعه ونبدل، وبالتالي نستعمل معادلات معقدة في البلازما بحيث نوجهها لطريقة أخرى باش نتفادى الروكت مثلا. بالتالي مش السرعة فقط، هي حتى السيكوريتي نتاعي يلزمني بسرعة نحميها. هذه شيء باش نعمل كونسبت نستحق معادلات معقدة جدا، فالكوانتم كمبيوتر ممكن يسهل لي الحسابات بسرعة كبيرة وبدرجة أدق. فهمت؟ فهذا من الاشياء اللي هما كل التكنولوجي تراهم الكل يعتمدوا على الكمبيوتيشن، على باورفول كمبيوتيشن. فالكوانتم كمبيوتر هو وسيله انا نستحق اداه لتسريع الحسابات. فبلازما روك الكنترول اول اللي عملته برزنتيشن از الدي ان اي كريسب اتسيترا يستحق باش يعمل حسابات معقده جدا وفي وقت يعني طبيعي قصير. فبالتالي الكوانتم كمبيوتر هو بوتنشال يجي يساعد في التطوير هذا.
واضح.
انا
واضح.
اعطيت اكزامبل على التكنولوجي
استاذ
تطلب.
حسين عنده سؤال. اتفضل استاذ حسين. استاذ حسين بيسأل ازاي بتطبق الهايزنبرج برنسبل على الكوانتم كمبيوتر.
انا ما طبقش. هو بالنسبه لي له انا استعمل الكونسيبت بتاع انا لما الكوانتم كمبيوتر نستخدم الفينومينا بتاع الكوانتم. فبالتالي بغير ما نشعر موجود اون سيرتين برنسيب. يعني انا لما لما نستحق الكوانتم كمبيوتر اي كونسيف ذا كوانتم كمبيوتر اي شود تيك ان كونسيدريشن الفينومينا الفيزيكال فينومينا. فيعني لما انا نعمل ديفلوبمنت نتاع اي كوانتم كمبيوتر all the phenomena of quantum physics should take in consideration. فهو باش ياثر في تطوير، معناها مش باش ياثر بتاتا بالطريقه اللي تراها انت. يعني كيف نطبق ماهيش حسابات. هو انا نعمل اي ديزاين كيوبيتس، اي ديزاين كوانتم كمبيوتر اللي هو خاضع للظواهر الطبيعيه والقوانين بتاع الكوانتم ميكانكس، منها البرنسيبل بتاع الانسرتينتي. ففي هذا يلزمني لما نعمل ديفلوبمنت مثلا في الكوانتم كريبتوغرافي، كوانتم تليبورتيشن، الاشياء هذه بطريقه معينه، وقتها كان ميك ذا ميجر، وقت نعمل ميجرمنت اتسيتيرا شو البيك باش يدخل بطريقه وباخرى بصفه ناتشورال. ما مش انا نحاول وين نجم نطبقه، بالعكس هو حيدخل بطريقه عاديه. لانه كما تقول انت انا عندي سياره وتمشي على الطريق، ففريكشن موجوده، يعني هي بطريقه عاديه، هذه موجوده بطريقه واضحه. لما انا ناخذ بعين الاعتبار اذا كان السياره الفريكشن باش تنجم السياره تبتدأ، ولكن وي كان نيجلكت الفريكشن اذا كان تمشي السرعه قويه وما نستحقش بريسيجن عاليه. فهو فما فينومينا يدخل انا حناخذه في بعض الاحيان بعين الاعتبار، في بعض الاحيان ممكن ما ناخذوش بعين الاعتبار، ولكن يلزمني نعرفه اللي هو يمكن ياثر على تطور السيستم ككل، او ياثر على الكونسيبت نتاعي ككل. فهو ما هوش ماثيماتيكال اي ويل ابلاي ذات وين جاي بالضبط. انا ما اعرفش هو القواعد الفيزيائيه لما انت تستعمل سيستم في كل حاله يمكن يظهر قواعد اللي تحد لك من البوسيبيليتيز نتاع رياليزيشن. فمثلا في الكوانتم كمبيوتر كوانتم رام تعرفها ان هي النون كلونينج تيوريم. مثلا النون كلونينج تيوريم هو بيعملنا حدود معينه باش مش نستعملوا الكلاسيكال رام الكلاسيكال ميموري، يلزمنا نستعملوا حلول مبتكره تو ايفويد النون كلونينج تيوريم مثلا معناها في نفس الشيء. انا بصراحه ما نستحضرش اكزامبل واضح، ولكن كل الكونسبتس نتاع الكوانتم ميكانكس واللوز نتاع الكوانتم ميكانكس هما يلزمهم يكونوا ناخذوهم بعين الاعتبار لما نطوروا في الكوانتم انفورميشن بطريقه او باخرى. من نفس الشيء في الفيزياء. في الفيزياء انت عندك محاذير معينه، مثلا انت وقت تعمل حساباتك في الفلويد ميكانكس ولا في غيره عندك محاذير معينه لازم تنتبه لها. فمثلا انت لما تقول لي لاميناريا فلويدز عندك محاذير في الفيلوسيتي والفيسكوسيتي، فبالتالي اذا كان ما تنجمش تطبق اللاميناري فلويدز كونسبت على اذا كان فلويديتي عاليه ولا عندي توربulent بروبلم. فهذا هو المحاذير اللي لازم ناخذوهم في كل مره لما تستعمل لما تعمل ديفلوبمنت في الكوانتم فيزيكس ولا في الفيزياء بصفه عامه.
Thank you Professor Hisham. Thank you for this interesting lecture. Thank you. طب دلوقتي بريك ونبدأ إن شاء الله الساعة 1 إن شاء الله.
شكرا.
السلام عليكم بروف.